In this video, we'll solve another type of equation, and that is an equation containing radicals. A radical equation is an equation that contains one or more radicals with variables in the radicand. For example, a radical equation might be the square root of 3x minus 4 is equal to 7, or the cube root of 2x plus 1 is equal to 3. So the radicand is the expression inside the radical. In the square root of 3x minus 4 equals 7, the radicand is the 3x minus 4. In the equation cube root of 2x plus 1 equals 3, the radicand is 2x plus 1. So our goal in solving these radical equations is to clear the radicals from the equation, because we need to get an equation where we can solve for x, right? To get x equals some number. And to do that, we are going to apply some properties. The first property of radicals states that if the nth root of x is a real number, the nth root of x to the n is equal to x. If I have, for instance, the square root of 25 and I square it, right, n is actually understood to be 2 for the square root. It's called the index. We don't write it, but it's understood. Well, the square root of 25 is 5. If I square it, I just get back to 25. Right, the square root of 81 squared. The square root of 81 is 9, but when I square it, I get back to 81. So we can skip that intermediate step. Right, the square root of 144 squared will just be 144. The square root of 2,578 squared will be 2,578. This also applies to algebraic expressions. If I have, for instance, the square root of x plus 1, and I square it, assuming that the square root of x plus 1 is a real number, then I just get x plus 1. Right, the square root of 2x minus 5 squared will just be 2x minus 5. This also works with other values of n. For instance, if I have the cube root of 8 and I cube it, well, the cube root of 8 is 2, cubed is back to 8, right? So if I have the cube root of 9x plus 4 and I cube it, I will just get 9x plus 4. So for the purpose of this book, we will assume that the nth root of x, or the nth root of that expression, is a real number when we are applying these properties to solve the radical equations. Another property of radicals that we will apply is that if you have two expressions equal, so if a equals b, then a to the n is equal to b to the n. This will enable us to do something to each side of the equation to eliminate the radical. And we just saw in the previous property, if we square a square root expression, we eliminate the radical. So we will be able to then square each side so that we can get a related equation. There's an issue, though, that we have to be careful about. And let me start with a pretty basic equation. Let's just say if we have x is equal to 2, for instance. The solution set of that equation is just simply the set containing 2. Well, by this property, this states that I can raise each side to the same exponent and get a related equation. So if I square each side, I get the equation x squared is equal to 4. This is a quadratic equation that I can solve by applying the square root property, which states that x is equal to plus or minus the square root of 4 plus or minus 2. So the solution set of this squared equation is negative 2, 2. So we started with an equation. When we squared it, notice how the solution sets of those two equations relate. The solution of the original equation, 2, is contained in the solution of the squared equation. but we got an extra solution. And so when we square or apply this property, we have to be careful to watch out for extraneous solutions. Remember that extraneous solutions are those solutions that arise through the process of solving the equation, but they may not work in the original equation. And in the text, I have a picture of a cave. If you think about this radical expression being a cave, we have to be careful what's inside. And so just help you think about that as a way to mentally remember that I have to check for those extraneous solutions. So the steps to solve a radical equation are these. We first isolate the radical expression to one side. If there's more than one radical, we want to isolate one of the radicals to one side. Then we will raise each side of the equation to an exponent equal to that of the index of the radical. So that's applying this property 2 that states that if I have the square root equal to a number, then I'm going to square each side. And the key thing here is, again, to remember that this index of the square root is understood to be 2, so we will square each side. If I had the cube root of an expression equal to some number, then I'm going to cube each side. And by the way, it doesn't have to be a number. It could be an algebraic expression on the other side. And then we want to solve the resulting equation. So in this particular case, we're going to get either a linear equation or quadratic equation that we need to solve. If the equation still contains a radical, then we would repeat steps 1 and 2. Lastly, we will check possible solutions in the original equation and exclude any extraneous solutions from the solution set. So here's an example. The square root of 3x plus 1 equals 11. My radical is isolated. I need to get the x outside of the radical, and the property that enables me to do that is to square each side. Squaring the square root of 3x plus 1 gives me 3x plus 1. Squaring 11 is 121. We have a linear equation I solved by subtracting 1 from each side. So 3x equals 120. And then divide by 3 to get 40. And then this is a square root equation. I need to check my solution in the original equation. I will substitute 40 in place of x to get 3 times 40 plus 1. And I'm asking myself, is that equal to 11? And inside, 3 times 40 is 120, plus 1 is 121. And the square root of 121 is 11. Therefore, the solution set is the set containing 40. Example B, I have the square root of x plus 12 plus 8 equals x. The first step is to isolate the square root expression. So I have the square root of x plus 12 is equal to x minus 8. Right, I have to subtract 8 from each side. And now we have the radical isolated. To remove the radical, I have to raise each side to the exponent of 2. So on the left, I have the square root of x plus 12 all squared is equal to x minus 8 all squared. Well, the square root of x plus 12 is just x plus 12. When I square x minus 8, recall that's really x minus 8 times x minus 8. I will get a trinomial when I square that. I get x squared minus 16x plus 64. So this is a quadratic equation that I need to solve by factoring. I need to set one side to 0 by subtracting x and subtracting 12 from each side. This gives us the equation 0 is equal to x squared minus 17x plus 52. And now I need to find the factors of 52 whose sum is negative 17. And I believe that would be negative 4 and negative 13. factored equal to 0 means we can set x minus 4 equal to 0 or x minus 13 is equal to 0. Solving, we get x equals 4 or x is equal to 13. Now that we have our solutions, we're not done. We have to check to make sure that these solutions are not extraneous solutions. 4 and 13 do solve this quadratic equation that we found, but they may or may not solve the original equation. So we just need to check by substituting these values in place of x in the original equation. If we replace x with 4, we get the square root of 4 plus 12. Then plus 8, is that equal to 4? This gives us a square root of 16 plus 8. Is that equal to 4? And no, because the square root of 16 is 4 plus 8, and that is 12, which is not equal to 4. So we have to discard this solution of 4. When we replace x with 13, we get the square root of 13 plus 12 plus 8. Is that equal to 13? And this is the square root of 25 plus 8 equals 13, and that is 5 plus 8, which is 13. So the 13 checks as a solution, whereas the 4 does not. Therefore, the solution set is the set containing only the 13. If you had to answer on a test, are there any extraneous solutions and what are they? You would say yes, 4 is an extraneous solution, but the actual solution set is the set containing 13. And then we have the equation, the square root of 2x plus 5 equals the square root of 3x minus 10. This equation has two radicals, but each radical is isolated to one side. Therefore, we can apply the property that if we raise each side to the exponent of 2, we can eliminate the square roots. So we square each side to get the square root of 2x plus 5 all squared is equal to the square root of 3x minus 10 all squared. Squaring the radical eliminates it, so we get the equation 2x plus 5 is equal to 3x minus 10. This is a linear equation. We collect our variables to one side by subtracting 2x from each side to get 5 equals x minus 10. You could have subtracted 3x from each side, that's fine too. But then we will add 10 to each side. So 15 is equal to x. Because this is a square root equation, we need to check. Replace x with 15. So we get in the original equation the square root of 2 times 15 plus 5. Is that equal to the square root of 3 times 15 minus 10? Inside the left radical, we get 2 times 15, or 30, plus 5, so the square root of 35 is equal to the square root of 3 times 15 is 45, minus 10 is 35. So we get a true statement, right? The square root of 35 equals the square root of 35. Therefore, the solution set contains the number 15. And then the last example that I have is the cube root of 2x minus 1 plus 8 equals 5. So we need to isolate this cube root of 2x minus 1 by subtracting 8 from each side. This gives us a cube root of 2x minus 1 is equal to negative 3. Then we'll apply the property that states we need to raise each side to the power that is equal to the index of the radical, which is 3 in this case. So we have the cube root of 2x minus 1, and then we'll cube it, is equal to negative 3 cubed. Cubing the cube root of 2x minus 1 gives us 2x minus 1 equals negative 3 cubed is negative 27. We have a linear equation to solve by adding 1 to each side to give us 2x equals negative 26, and then dividing each side by 2. we get x is equal to negative 13. And then we can check. In the original equation, replace x with negative 13. This gives us the cube root of 2 times negative 13 minus 1 plus 8. Is that equal to 5? So this is negative 26 minus 1, which is the cube root of negative 27 plus 8. Is that equal to 5? The cube root of negative 27 is negative 3 because we're asking ourselves what do we need to cube to get negative 27, and that is negative 3. This gives us negative 3 plus 8 equals 5, which is a true statement. 5 equals 5. Therefore, negative 13 is the solution of the equation, so the solution set is the set containing negative 13.